Hi everyone, welcome to our third lecture in the reinforcement learning course. I'm Diana. I'm one of the other lecturers of this course alongside with Hado and Matteo. A bit about myself before we begin. I'm a research scientist at DeepMind and been there for almost 4 years now. Prior to joining DeepMind, I was a PhD student at UCL, and about 10 years ago I was taking the machine learning master course at UCL, including this particular course. I've been involved with the RL course for the last 5 years, first as a TA and then as a lecturer. That's a bit about myself. Now to the actual content of today's lecture. Today we're going to be talking about Markov decision processes, which are a way of formalizing the RL interaction loop, as well as the objectives that arise in RL and the class of problems that we can encounter, like policy evaluation and control. Finally, we're going to look at the full class of iterative model to tackle these problems. And these are known as under the umbrella name of dynamic programming, and we'll see in a minute why that is the case. Okay. First, background reading. The topics that we're going to cover today are also covered in the Sutton Barto book in chapter 3rd and 4th. So I would encourage you to read those chapters alongside with this lecture. A bit of recap from last week. We've seen that the reinforcement learning is the science of learning to make decisions in the environment. We also learned that the RL system comprises of an agent and an environment. The agents can learn a policy to behave in the environment, a value function or model of the world. The general interaction between the agent and the environment usually unfolds in time, and the decisions that we're making have long-lasting consequences that would affect the reward that we're going to see in the future, that can change the state of the agent, but also the change can affect a change in the environment state. Okay, so last lecture you've seen a very small instantiation of this system with an RL problem that only has one state but multiple actions. In this lecture, we're gonna be formalizing the full RL problem with its sequential nature. We're gonna talk about the first class of solution methods, which assumes that we do have a true model of the environment. So everything that we need to know about this interaction between the agent and the environment to predict the next states of the agent and the environment, as well as the reward associated with these transitions, are given to us. These methods are called dynamic programming. And although in this week, both lectures will be targeting MDPs and dynamic programming, so full knowledge of the environment. In the next lecture, we will see how these ideas and this principle of dynamic programming can be relaxed to the case where we, instead of having true access to the model, we only have access through sampling, through interactions with the world. Okay. First item on the agenda, formalizing the RL interaction. So we're going to discuss a mathematical formulation of the agent-environment interaction. This is called the Markov decision process, and this enables us to talk more clearly about the objective of an RL agent and how to achieve it. First, a simplifying assumption. For now, we're going to assume that the environment is fully observable. That is, the current observation that the agent sees contains all the information relevant to make all predictions in the future. Note that almost all RL problems can be formalized as MDPs, so this is a very encompassing paradigm. These are just a couple of examples. Things like optimal control problems in continuous MDPs are still covered by this formalism, although in this particular lecture and for most of the exposition of the theory, we would be assuming finite and discrete action space and state spaces, but all of these can be naturally translated to the continuous case. The other example is partially observable problems. Although this seems to violate this first assumption we made, we can show that even these models can be converted into an MDP given the right history. I mean, even things that you've seen last week, which are banded, can be formalized as an MDP with just one state. Without further ado, this is the definition of a Markov decision process as presented in the book. So Markov decision process is a tuple that contains the set of all states, the set of all actions, this probability kernel, which describes the joint probability of what's going to happen in the next state. So given that we are in state S and have taken action A, what am I going to observe at the next state? So what's my next state S prime, and what kind of reward signal am I going to be rewarded for that transition? And the last element here is the discount factor, which trades off later rewards that we'll see in the future with earlier ones by discounting them heavily or not. Okay, we're gonna call P the dynamics of the problem, or the transition dynamics. And it's good to notice that sometimes it's useful to marginalize out some of these quantities, like the state transition and the expected reward. These are the two equations here. So this is just looking at the transition to the next state, and this is looking at all of the reward that we could expect from a transition starting from state S and having taken action A. And this leads us to the alternative definition of the MDP, which is quite prevalent in literature. So we're mentioning here because most likely in a lot of the papers and other books like Chavas Febivari's book, you will see a similar definition. So the only difference here is that now the transition kernel is this marginalized transitional kernel, which looks only at what's the probability over my next state, given that I've started in S and taken action A, and R, as given in the definition of this MDP, is the expected reward associated with that transition. So although this random variable might depend on where we end up, in the definition of this MDP, we assume that we have access to the expected version of this quantity. Okay, and then the discount factor remains the same. Note that these formulations are equivalent. There are no additional assumption or removing any assumption, and we will be using them interchangeably depending on when it's more convenient to use one notation versus the other. Okay, now the Markov in the Markov decision process comes from the Markov property, and you might have seen this previously in something like hidden Markov models or in a lot of the sampling methods. This property really says that the future is independent of the past given the present. And for MDPs, this is a property that all states will have. And what does it mean for a state to have the Markov property? Well, a state S has the Markov property if it summarizes basically all of the history that it has, all of this history that has come before it in terms of the prediction value of the next state or the next states in the future. So this is a different way of saying this is that the state captures all the information, all the relevant information for the prediction problem captured in the history, or another way of saying it is that once the state is known, the history can be thrown away. And a different way of saying this is that the state is a sufficient statistics of the past. So anything that has happened in this interaction process is summarized in terms of its information about the about future transition is summarized in the current state, in the current observation. Okay, this is just a bit of a test to see if you understand the principle and what that means in an MDP. These are a couple of statements that I've written down. Some of them are true, some of them are false. I would encourage you to pause the video here and go through all of them and see which of them are false and which of them are true. Welcome back. Hopefully you managed to go through this exercise. We're going to just go very quickly through the results. Okay, so the principle here is that the state at current time step contains all the information necessary for all future predictions. Anything that has happened prior to time t is not relevant because all the information is captured in ST. That means all the information, all including AT-1, is contained in this state. So anything before that does not matter. So that means that these two are completely equivalent. The same thing here. These things have happened before ST. So because all the information is contained in ST, we can safely remove them. Now, this one, again, all the information here is contained in ST, but AT comes at the same time or after we observe state ST. So this is additional information. The action that I'm taking at state S conveys more information and will determine or skew the distribution of what I'm going to observe in the next state. So this one is false. And this one, the fourth one is the same as 1 and 2. All the information here is contained in this one, and these are just predictions for the future. Whether or not that is state or reward functions or actions or anything that pertains to the future is fully conditioned on the current state. So this one is true as well. Okay. So we've seen that we've argued that MDPs are a good way of formalizing an RL problem, and let's look at an example of doing such. So this is an example of a cleaning robot. This is from the Sutton and Bartow book, chapter 3. This is a robot that its goal is to clean soda cans. For simplicity, it has only two states, a high battery state and a low battery state. And it has three actions. One is wait for someone to put a can into its bin. The second action is search, which means that it will actively search for soda cans in the environment. And the third action is recharge, which will enable it to get the battery from a low state to a high state. And for this particular example, we're going to assume that the reward associated with searching is actually higher than the reward associated with waiting. So if it's actively going into the environment and trying to search for soda cans, its expected return, which is the collected number of cans, might be higher or is higher than just waiting for someone to put cans into its container. And then we have some stochastic dynamics, where with alpha probability we can loop into a state of high battery, and with 1 minus alpha probability we're going to transition from a state of high battery into a state of low battery, at which point we would need to recharge. Okay, this is just a full table depiction of the MDP, and we'll see in the first definition of the MDP as a tuple of state, actions, joint transition, probability, and discount. The discount for now can be 1. And the states are just the ones that we've discussed, high and low. The action space is search, wait, and recharge. And then the joint transition kernel can be just read off from this table. So for starting in state high battery and taking the action search, you have alpha probability of ending up in a state of high battery and achieving a reward for that transition of R search. Okay, so this is pretty trivial write-off. Okay, for the other definition of the MDP, we have the same thing, state, action, those remain the same. Now the probability kernel in this formulation is just this one, the transition to the next state, and then the reward that we have in this definition is actually a reward that is RSA. Okay, and this one is not exactly read off from the table. We would need to make a bit more computation there because the reward in this particular example depends on where I ended up on that transition. And this reward that we have in this definition only condition on the state of action. So if we would go for this definition, in order to specify this MDP, we would need to compute the expected reward seen on this transition. So for instance, for these initial conditions, high battery and search, this would be with probability alpha, I'm gonna end up in a state of high battery and receive reward R search, and with 1 minus alpha probability, I'm gonna transition to a state of low battery but still receive the same reward. So because in this particular example, regardless of where I'm transitioning, I'm gonna have the same reward. The reward associated with this transition is actually R search. That might not always be the case. So for instance, for this particular example, when I start with in a low battery state and I choose the action search, with 1 minus beta probability, I'm gonna have a reward of -3, and with beta probability, I'm gonna have this R search reward. So the probability, the reward associated with low and search would be 1 minus beta plus R search. So in order to get this definition of the MDP, or to go for this definition of the MDP, you would need to compute these quantities. Okay. Okay. Now the last thing I want to mention on this example is just to show you a graphical representation of the MDP. This is something that we would normally use to depict an MDP. So we have the states, a high and low battery, as nodes of this graph, and then we have arrows that code the transitions between these states, and these are annotated with the probability of transitioning from one state to the other and the reward associated with that transition. Okay. Now to formalizing the objective of an RL agent. In order to do that, we're going to be introducing returns. So we've seen that in acting in an MDP, the interactions at every point in time would result in immediate rewards, and these lead to returns. And returns have at least 3 different returns that we're going to be looking at. Are undiscounted returns, which is the sum of all the rewards that you're going to see in the future. the discounted return, which uses this discount factor that we've seen in the definition of the MDP to gradually discount the rewards that you see in further steps in time, and the average reward formulation that looks at the average reward. So depending on the MDP, one of these might be appropriate. For instance, the undiscounted return is usually used in episodic finite horizon problems, because if this becomes this is undiscounted and becomes an infinite sum, this might be unbounded. The discounted return is the one that we're going to be using the most frequently, and it is suitable for both finite and infinite horizon problems. And average reward usually is used for continuous infinite horizon problems. Note that all of these G's are random variables that depend on both the MDP, so the stochastic transitions in the probability kernel, and the policy that that we're employing in order to see these rewards. Okay. So as I said, our choice here in most of the most popular choice of return in the literature is the discounted return. Moving forward, we're gonna be using this for both finite and infinite horizon problems. And this is just the same discounted reward, but for the infinite horizon problem. Okay. And the discount, which is a number between 0 and 1, means that the marginal value of receiving rewards after k plus 1 time steps is actually modulated by gamma to the k, which can be a very small factor. Remember, this is a number that is less than 1, so immediate rewards will have a more high weight on this return than delayed rewards. For instance, if the gamma is close to 0, or if you put gamma to 0 in this expression, you would see that the return at in this particular example is just the immediate reward. For values close to 0, this gamma to the k decays very, very rapidly to 0. So we call this return myopic, because it only considers, or most of the values it considers come from immediate rewards. To the opposite side, if gamma is close to 1, this is far-sighted. So in the limit there, if gamma is equal to 1, we've seen that this is the undiscounted return that weights equally all the rewards that we would see in the future. Okay, why discount? There are two sides to this problem. One is problem specification. It might just be that the MDP you're considering actually has this property that immediate rewards are actually more valuable. Think of it as interest rates. And it's also something that we see in animal human behavior, that there is a preference for immediate reward. In a sense, it's leveraging the probability of actually making it to 10 years time or 100 years time and seeing rewards in that far horizon. And then on the other side is the solution side. So sometimes even when we're interested in a undiscounted version or almost undiscounted version, is mathematically convenient to go for the discounted reward case. And this also avoids the infinite return that we can get in cyclic Markov models. So if the horizon is infinite, the undiscounted return might not be bounded. So maximizing over it might be problematic. So the way to think about it right now is that the reward and the discount factor together will determine the goal of the agent and the goal of the MDP. The goal of the agent is to find a behavior policy that maximizes this return. And as I said before, this G is a random variable that depends on the MDP and the policy. So what we want is a behavior policy that maximizes the expected value of this return. And a policy is mapping that for every state assigns for each action in the probability set a probability of taking that action in that particular state. And this is the notation that we're going to be using. For deterministic policies, we sometimes use this other notation, AT equals pi st, which basically denotes just the action that is taken deterministically by that policy. And because we're going to be looking at expected values of the return, we're going to be introducing some quantities to help us refer to this expected value. So we're going to be introducing the value function at a particular state S, which is now the expected return that we're going to get starting from state S and following policy pi. And similarly, we're going to be introducing the Q value, or the state action value, which is exactly the same expectation, but now we're starting in state S. We're taking action A, and after that, for all of the other steps, following and behaving according to policy pi. And there's an intimate connection between these two, which is noted here, that the value function is the expected state action value under the policy that we are evaluating under pi. Okay. Now we're going to be introducing the optimal value function, and the optimal value function is just the function that for every state maximizes over these quantities previously introduced. So all of these quantities, the value function introduced here, V and Q, are dependent on a policy that we're going to follow after this state, or after this state and action. And the optimal policies are looking at, for every state, it's looking at all of the policies that we could employ in the future, and is doing a maximization over all of these policies. And the same for the action value function, the same interpretation. We're at state S, taking action A, and after that we're looking at all the possible policies that we might be able to employ in the environment after choosing action A, and maximizing over those policies. So the optimal value function specifies the best possible performance in the MDP, and we're gonna say that an MDP is solved when we can provide the optimal value function. And we'll see that if we provide the optimal value function, we can trivially derive an optimal behavior policy out of that. Okay? So in terms of optimal policies, it's good to notice that there's a partial ordering in the policy space, that and we're going to say that a policy pi dominates a policy pi prime if for every state in the environment the value associated with that state is under policy pi is greater than the value associated with the policy pi prime. And the theorem that we have in terms of optimal policies is that there's always exists a optimal policy pi star. This is how we're going to be denoted it, that is better and equal with respect to all the other policies in the environment. So this is a policy that will dominate for all states in the environment all other policies. Okay, and for all of the policies, they achieve the same value function and the same action value function. So any policy that is optimal will achieve the optimal value function and will achieve the the optimal state action value function. Okay, I'm gonna pause a bit here because that's a lot to take in. Okay, now I've prefaced that if we know the optimal value function, in particular, if you know the Q optimal value function, we can derive an optimal policy, which is just the greedy with respect to that policy. So this policy will choose with probability 1 the maximum action according to Q star, and put 0 probability on all other actions. So it's gonna look at the values of Q star, and it's gonna act greedily with respect to that. And this will give us an optimal policy. I'm not going to show this here, but we will see a proof of that moving forward. Okay, a couple of observations here. There's always a deterministic optimal policy in the MDP, and the statement above implies that once we have a Q star value, we can immediately have an optimal policy. In general, there might be multiple optimal policies, and some of them might be stochastic. Okay, moving on, we're going to be looking at the Bellman equations. These are a very central concept in RL, so this is something important. Okay, and the Bellman equations actually describe the recursive nature and the structure that that is present in the value function we've just defined. So we're gonna start here with the definition of the value function for a policy pi, which is the expected return that we're gonna get starting from state S, and we're gonna expand this recursively. So this is the reward that we're gonna get at the next step, plus what's gonna happen in the future. So this is the return at the next time step. This expectation is over the whole process, so we're unfolding this in time, and we can rewrite this as the immediate expectation over the next transition and the value function, which is already an expectation of what's gonna happen after t plus 1. So you see we have v pi at time t on this side, and v pi at time t plus 1 on this side. So there's a recursive nature of the relationship, and this is just spelling out exactly this expectation. So it's the expectation of taking action A in state S. This is this part, and then what's going to happen in the transition. So I started in state S. I've taken action A, and I've transitioned to state S prime, and I've been rewarded R. So this is the transition kernel, and we're gonna weight all these potential transitions to R and S prime by their return. Okay. So the same thing can be done for the Q value, and the derivation is just here. So we do the same thing. We expand for the first step, and then this we've seen in the previous step that this is the value. This is just the value function associated with st plus 1, and this is an expectation. This itself, it's an expectation over this Q value function when AT+1 is chosen according to policy pi. And this is just spelling out that expectation. So this is the V that we've seen before. And this is spelling out just how these two states and actions relate to each other. And of course, there's an intimate connection between these two value functions that we're using for this particular step. That the V is an expectation over the Q values. Okay. So these recursive relationships are very important and are known under the name of Bellman equations. And particular, these are known as the Bellman expectation equation because it's an expectation over the policy that we're employing. Now, we also have another set of equations which are Bellman optimality equations, which describe the optimal value functions. So we can say that the optimal value functions satisfy this equation. This is very similar with the ones that we've seen in terms of expectation, but instead of having an expectation over the next action here and here, there's a maximization over actions. And this is because of the optimality. And let me give you some intuition why these the optimal value functions might satisfy this equation. Okay, let's remind ourselves that the greedy policy with respect to the optimal value function, so V star or Q star, is an optimal policy. I haven't proven this, but we've stated this before. So this greedy policy that takes the max over these values gives us an optimal policy. Now, if you apply the Bellman expectation equations, we know that the value function, the Q value function corresponding to this Q pi, which is an optimal policy, adheres to this equation, and this part here, the expectation under this policy, actually comes down to being the max over the optimal value function. Okay. So this first part is just rewriting the Bellman expectation equation for pi star. And this is just taking into account the definition of pi star as the max over Q pi. Okay? Which means that we get this expression, which is exactly what the optimal Bellman equation says. And the same thing can be done for V. Okay? Cool. Now, let's look at solving problems in RL using the Bellman equations. Okay. First, we're going to be introducing the two classes of problems that we encounter in RL. First class of problems are called policy evaluation or prediction, which is estimating the values of V pi or Q pi. So this is answering the question, given a behavior policy, given this pi, what is my expected return under this behavior? So if I were to employ this policy, what am I expected to get? So given this treatment protocol or this trading strategy, what is my expected return under my reward specification? Now the other class of problems are control problems, where we're trying to estimate the optimal value function, either V or Q, and this leads to an optimal way of behaving. So the purpose for this class of problem is to find an optimal way of behaving, or to find the optimal policy. So things like, what is the optimal treatment protocol, what is the optimal control policy to minimize time on the road or fuel consumption, whatever the reward is. So one is about, given a behavior, I'm gonna try to estimate how good is that behavior on average. The other problem is a much harder problem, where we're trying to go for the optimal value functions and the optimal behavior. Okay. So we're gonna look here at a very small example. So we're gonna consider this MDP, this graphical representation, 3 states. We have 2 actions. A1, which is kind of right, but once you are at the end of the state space, you transition back to the starting state. And action 2, which is roughly left, but again, when you're at the end of the chain, you transition back to S0. All of these actions, if they are taken, have a probability of 0.9 to succeed. So if I'm taking action 1 in state 1, I'll have a 0.1 probability of transitioning to S0, but I would have a 0.1 probability of just looping back and staying in that state. Okay, for all transitions that end up in state 0, so at the beginning, so this one, and the transition to itself, the reward is 0. For all other transitions, the reward is -1. And now we're gonna be looking, you're gonna be looking actually at an evaluation problem. For this particular MDP, consider the discount factor 0.9, and your task is to find the value function vpi associated with a policy that always in this MDP takes action 1. Okay, and the same question for now a uniformly random policy. And the last question here is doing both of these evaluation problems, but now with a discount factor of 0 rather than the original discount factor of 0.9. Okay. So I would encourage you to pause the video here to work out this example before we move on. Okay, hopefully you've managed to go through the example. I think this is a nice way of testing your understanding of both defining an MDP based on the graphical representation, then formalizing the returns and computing the value functions. So combines all of the concepts that we've covered so far, and hopefully it gives you a taste of the complexity of the problem of estimating these quantities, even for the easier problem of policy evaluation. Okay. I'm going to give you a solution rather than a solution, a way of reaching a solution, or a way of tackling policy evaluation for these small MDPs. And this will be done via rewriting the Bellman equations into matrix form. So for every state in the environment, we have a Bellman equation associated with that state, and that transition to the next state. And for each state and action pair, we would have the same for the Q values. For now, we're gonna just focus on computing the value function for a policy pi, and for that we're gonna just collect all the Bellman equations for all the states in the environment into a system of equations that can be rewritten in this matrix form. So this leads to this matrix Bellman equation for the expected return under policy pi, and these are now vectors v and r, and this matrix is the probability transition from state I to state j under the transition kernel of the MDP and under policy pi. So just to write this out, this is the probability of starting in state Si, taking action A, and transitioning to a state Sj. This is what we have from the definition of the MDP, and this is weighted by the probability of taking this action A in state Si. And so this is the expected probability of transitioning in this state starting from Si via acting according to policy pi. And the same thing for the expected reward under policy pi. This is the expected reward, instantaneous reward that we're gonna get, considering we're starting in state Si and we're gonna behave according to an action chosen from policy pi. Okay. And once we have this formulation in matrix form, this is just a linear equation. So we can solve for v, and you can see that this involves inverting this matrix. That is 1 minus lambda p pi, which is this probability matrix of transitioning from one state to the other under policy pi. Okay, so that's it. Note that the computational complexity of this is number of states to the power of 3. Even if there are other solutions that are not cubic in the state space, it's really usually more than to the power 2 of the state space. So this is a feasible solution only for small problems. Fortunately, for larger problems, larger state spaces, we have iterative methods like dynamic programming, which we're going to see next, or Monte Carlo evaluations, and temporal difference learning methods. Okay, now this is a solution for the evaluation problem. You could try to employ the same principle for the Bellman optimality equation in order to get the optimal value function, but note that the optimality equation is non-linear, so you won't get a linear system of equations. So this kind of reasoning does not trivially go through for the optimality case. So we can't use in general this matrix formulation to do control. Okay, but nevertheless there are many iterative solutions. The ones that use models like dynamic programming, which we're going to see next, and the algorithms there are policy iteration and value iteration, and other iterative methods that do not assume knowledge of the model and are using samples like Monte Carlo methods, Q-learning, and SARSA, which are temporal difference learning methods. With that, we're gonna be transitioning into dynamic programming. Dynamic programming refers to a class of methods that try to learn the optimal behavior of the optimal value function given a true model of the world, the true model of the MDP. The term was actually coined by Richard Bellman to describe his research, and his reasoning is as follows. The 1950s were not good years for mathematical research. I felt I had to shield the Air Force from the fact that I was doing mathematics. What title, what name could I choose? I was interested in planning, in decision making, in thinking. But planning is not a good word for various reasons. I decided to use the word programming. I wanted to get across the idea that this is dynamic, that this is time varying. I thought, let's kill two birds with one stone. Let's take a word that has a precise meaning, like dynamic, in the classical physical sense. It is also impossible to use the word dynamic in a pejorative sense. Try thinking of a combination that would make it possible to give it a pejorative meaning. It's impossible. Thus, I thought dynamic programming was a good name. It was something that not even a congressman could object to. So I used it as an umbrella for all of my activities. Okay, in nowadays, and the meaning of the word that we were going to refer to, the dynamic programming term refers to a collection of algorithms that can be used to compute optimal policies or optimal value function given a perfect model of the environment as presented in the Markov decision process definition. And we will discuss here several dynamic programming methods to solve MDPs. All of these methods actually have a pattern which involves two steps. One is policy evaluation and the other one is policy improvement. Okay. Let's start with policy evaluation. So we've seen already a solution to a policy evaluation problem. The exercise you solved before and the matrix manipulation that we've seen just prior to this is still a solution to this problem. Now we're gonna see a different way of computing the value function corresponding to the policy pi for an arbitrary policy. And the idea here is to turn this equation, the Bellman equation, into an update. And this leads to this following algorithm. We just initialize the values for all states in the MDP, and then we iteratively update these values according to this equation. So at time in the iteration at iteration k plus 1, the value of a particular state would be updated towards the reward that you're gonna see in the next step and the value function computed from the previous iteration at the next state. So this is using this equality that we know holds for the estimate we're trying to get to update towards that estimate. And the stopping criteria here is whenever the value function resulting from this update is the same as the one at the previous iteration for all states in the MDP, then we can stop. And also when this happens, we're guaranteed to have found V pi, because let's remind ourselves, V pi is the solution to this equation. So if you plug this in, if Vk and Vk plus 1 are the same, that means that Vk respects or obeys the Bellman equation for policy pi. Thus, because this is a unique solution, Vk has to be, and Vk plus 1 has to be equal to V pi. Okay. Does this algorithm always converge? The answer is yes, under appropriate conditions, when gamma is less than 1, and we will see a proof of this convergence and the conditions under which this convergence is possible in the next lecture. Okay, let's look now at an example of how policy evaluation works in this iterative setting. Okay, let me walk you through this example. This is a grid world example where the numbers in the grid represent the number of the states, and the action space considered are up, right, left, and right. And for all transitions in the environment, we're gonna be given a reward of -1. And these states, the gray one, are considered terminal states. That means that if the agents transition to one of these states, then the episode terminates at this point in time. We're gonna also be using a discount factor of 1 because this is episodic. We don't have any issues with the infinite returns. Okay, and we're gonna see what iterative policy iteration does in this particular example. This is just the algorithm that we proposed previously, this one. And let's go through the steps of updating the values according to this procedure. Okay, so first of all, we start by initializing the values at 0, for instance. Oh, by the way, we're going to be evaluating the uniformly random policy, which is the policy that assigns equal probability to the 4 actions we're considering here. So this procedure needs to converge to V pi, which is the value of this uniformly random policy. As you see, at the first step, we're just initializing V0 to be all 0, and after that, k plus 1, we're going to be updating values according to this equation. Okay, so just writing it here. This is expectation over the next transition, just the next reward, plus gamma v, the estimate at previous step, value at the next state. Okay, now we can simplify things a bit here, because this is 1 and this is -1 for all the transitions in the environment. So this is now expectation over -1 plus vk, and that means that this is 1 plus the expectation over the next state transition, st plus 1, for all of the values. In particular, for v1, this means that this is -1 plus the expectation of v0. We're always using the previous estimate of all of the values surrounding this state. Because all of the values at iteration 0 were initialized at 0, the expectation over this value would always be 0. So v1 for every state would update to -1, which is exactly what this matrix is. Okay, let's take this further to the next step. So for v2, we have a similar update. Again, this is the general update that we're following, simplified for this MDP. So it's still gonna be -1 plus the expected value of what's gonna happen in the next state. And now this k is 1. Okay, so for each state, we're gonna look at the state it can transition to under each of these actions. And because it's a uniformly random policy, so all these actions or all these states would be reached with the same probability, we're just going to average those values. So for instance, if we consider in this state, in order to compute its value, we're going to look here, what are its neighbors and where the actions would take it. So the right action will give it here, and this one will just loop back. So the up action will just loop back to the state. So the average value of these states would be -1, -1, -1, and 0 divided by 4, and this is -75. Okay, and the same computation can be done for any of these other states in the middle. These will have a value of -2 because the adjacent states there are all of value -1 and -1 from the immediate reward that we're getting, and so on and so forth. We can extend this computation further and further till this particular step where we reach convergence, which means that, and you can do this to convince yourself that if you apply this rule again, which is the update rule, for every state, vk plus 1 equals vk, for vk being this particular matrix. Okay, and that also means that vk has converged to v pi, which is the value of the uniformly random policy, which is the thing that we were looking for. Okay. Good. Now, another thing to notice here is that we can act greedily with respect to the values that we obtain in this iteration. In particular, if we consider this last iteration, so this one we've already converged, so this is the policy of the uniformly random the value of the uniformly random policy, and we can see that if we act greedily with respect to the values here, we can get a pretty good policy. Actually, we can get the optimal policy of behaving in this environment. So we have a very uninformative policy, a very bad policy in terms of behavior, because it takes every action randomly. It has no structure to preferring one action versus the other, so the value function is not too good. But based on that evaluation, doing an improvement step based on those values, a greedy improvement step based on those values, gives me a very good policy. In this particular case, this is an optimal policy. This is actually a very general principle in reinforcement learning and in dynamic programming, of evaluating a policy and then taking this greedification step, where the new policy that we're getting out of this greedification step is actually guaranteed to improve based upon the policy that we started with. So we start with the policy pi, we evaluate that one, and we get the policy pi new, which is a greedification with respect to these values. What we're saying is, if we're doing this this step, we are guaranteed to get the value that to get the policy that improves for each state over the policy on which the improvement was made. Okay, so this is the actual statement that for each state, and the same for the value functions, the state value functions for each state in action. Sorry. Okay. Let's go through the proof of that, but first I'm gonna try to give you some intuition why that is the case and why we're guaranteed to improve, and maybe then go a bit more into the mathematics of how to prove this. Okay, so first of all, by definition, this new policy is greedification, is the argmax of this evaluation. Okay, so given the Bellman equation, I'm just gonna write down the Bellman equation here for q pi. I have this. And by this notation I mean under. Okay, so the action at S prime is selected according to pi. Now, by the way actions are selected in pi nu, we know that this is greater or equal than the max. So the expectation is always greater or equal than the max. We still have an expectation, right? And this is actually new. Okay, so let me rewrite the statement. Okay. And what does this statement actually say? It's saying that if at the next state, if at S prime, I'm gonna be behaving with respect to this new policy, this gridification policy, pi nu, take an action with respect to that policy and then continue to follow policy pi. Just remember that this this expression actually means that I'm taking an action, a prime, according to this new policy, but after that I'm still following the old policy, right? So from t plus 2, I'm still gonna be following pi. So I'm saying I'm taking an action with respect to the new policy, and then I'm following my old policy. I know this combined policy that I'm doing right now is guaranteed to have a greater value than the policy that I started with. And this is the principle here. There's two things basically that pi nu can do. Either agree with the policy, where the previous policy, which means that the argmax there is already what pi was doing, or disagree with that policy, which means in that case means that if I'm deviating from that policy, I have an opportunity to improve. And deviating only once from that policy, as in here, already says that even if I don't do any other improvements and fall back on my previous policy, I'm still gonna improve. So in a schematic, this is, let's say, the decisions and the trajectory that I'm gonna fold under the previous policy that I have. This would give me some return, and I'm interested actually in the expected return. Every time I have a decision that disagrees, the pi nu disagrees with pi, then I have an opportunity of taking a step that is different from pi. And then I'm saying, if I've taken that step but still continue after that with pi, this return on average is going to be better than this one. And every time I deviate from this, here, I also have the same property. If I deviate, then and still follow the previous policy, I'm still gonna improve. And I'm still gonna improve over this one, which is already improving over that one. So every time I'm deviating from this policy that I've previously evaluated, I have an opportunity to improve more and more. So the more I deviate from this policy, the more opportunity for improvement I have. Okay, let's try to make this a bit more mathematically precise. So we've already seen that. I'm just rewriting this equation. Pi is greater or equal than RSA plus gamma expectation over the next state Q pi. This is the old policy, just to remind ourselves. Okay. Okay, and again, so the next state, we're just going to take a action corresponding to this new policy, and that's it. Oh, sorry, the inequality here is the other way. This is because this is a maximization. Okay, but then we can apply the same principle to this value function and say that this is greater or equal, less than equal than the reward that we're gonna get at the state, given that we've chosen this action corresponding to pi mu plus gamma expectation over, now this denotes the state after S prime of this is just applying exactly this equation and this reasoning, but now for not for S and A, but from S prime and whatever action was chosen by pi mu of S prime. Okay, and actually we can unfold this even further, and this actually would be an expectation over a trajectory that unfolds in time of SA plus gamma plus gamma. And if I unfold this, it's gonna be R of S prime prime mu of S prime prime plus so on and so forth. And this, if you remember the definition of the discounted return, is exactly the value function corresponding to pi mu SA. So we're in state S, we're taking action A, and therefore after we're choosing action according to pi mu. Okay, so this actually says that the value of the new policy that we've induced by choosing greedy action with respect to this estimate, if we evaluate that policy, we're guaranteed to get a better value function than the one we started with. Okay, and this is the greedy improvement principle. Okay, we can use this in what we call policy iteration algorithm, which is this iterative procedure between policy evaluation, building an estimate of the pi or q pi, and taking an improvement step with respect to this estimate, such as to produce a new policy that is better than the one we've seen before. And one instance of policy improvement step is the gridification step. There are other ways of improving your policy, but this is one of the most used principle and well-known principles in reinforcement learning and dynamic programming. And these are just depictions of how to think about this this policy iteration algorithm. We start with a value function and the policy. We evaluate that policy. Then we gridify with respect to that evaluation to get a different policy. Once we have this policy, we are doing this evaluation step again, and this is gridification. Again, this step can be just improvement in general, but the most common step of improvement, at least for value-based methods, is the gridification. Okay, and we're doing this this step till we converge, till the evaluation problem basically the greedy with respect to the evaluation problem gives you the same policy back, and at that point we've converged. And at that point, we do have the optimal value function, and the gridification with respect to the optimal value function would give us an optimal policy. Okay? Good. Let's look now at one example, one more realistic example of policy iteration. Okay, let me walk you through this example. This is a car rental example that has two locations, which are the states of the MDP, that have 20 cars, a maximum of 20 cars each. The actions are moving cars from one parking lot to the other, up to 5 cars, and this movement of cars incurs a penalty of -$2 per car. The reward, the other reward associated with this MDP is $10 for each available car rented. The discount factor that we're going to considering is 0.9. The transitions are as follows. Cars can be returned and requested at random according to a Poisson distribution. And the two locations have slightly different Poisson processes. The first location has on average 3 requests and 3 returns per day, while the second location has on average 4 requests per day and an average return of cars of 2. Okay, so this is a simple enough MDP. It's quite small, just 2 states and a handful of actions. The transitions are quite stochastic, but quite well behaved. At the same time, it's an MDP where I, for instance, can't read off what the optimal value function or what the optimal behavior should be, as opposed to the, I guess, examples that we've seen so far, where just by looking at the MDP or computing a bit the values in between, you can read off kind of what the optimal strategy is. Here is a bit more complicating to do that as a human. Even the evaluation problem. So for instance, if I'm given a particular policy, let's say if there are 5 cars in one of the parking lots and 15 cars in the other one, any car above 15, I should move to the first parking space. Any policy of this kind, I wouldn't necessarily know off the top of my head or with immediate calculation what the return associated with that would be. The dynamics of the environment are intricate enough that I can't compute that off the top of my head. So neither the evaluation problem nor the control problem are that simple or trivial. Nevertheless, if you look into the computations of the values, it's actually not a very complicated problem in terms of applying policy iteration. And this is exactly what happens when you do run policy iteration on this example. So as a reminder, policy iteration is this process where we start with the policy, we evaluate this policy, we take a greedification step or an improvement step with respect to this policy to get another policy. In this case, we start with random value function of 0 and the policy associated with that. We get policy pi1 by acting greedily with respect to the value of this uniformly random policy. And this is the evaluation of that policy, pi1, that was the greedification of the uniform one. Then we get pi2 by acting greedily with respect to this value, and this is the evaluation that we get after that, and continue this process. And we see that by the fourth iteration, or third iteration actually, this already has converged, and we have a stable value that is actually both the optimal policy, pi3 and pi4, but also the optimal value function. Okay, so this is a nice example of how quickly this thing can get to the optimal policy, even in non-trivial example. Okay, good. A couple of more observations on policy iteration. So again, this is the process of evaluating a policy and improving a policy and repeating that process. One of these steps is the policy evaluation step. And we've seen that this is not a trivial step. Computing the value associated with a particular policy can be quite an expensive procedure. So the question becomes, do we really need to run especially this iterative policy evaluation procedure till we converge to the actual B-pi or Q-pi? Or can we stop when we're maybe closer to that estimate and save a couple of iterations? In particular, can we simply stop after k iteration of iterative policy evaluation? And if you remember, in the small grid example we've seen before in the iterative policy evaluation, it was sufficient to run policy iteration for 3 steps to get to a value that would induce the optimal policy. Let's go back just for a bit to this was the example that I was talking about, and we started with random values, and by the third value here, by the third iteration of policy iterative policy evaluation, we can see that the greedy with respect to these values already gives you the optimal policy. You can see that we are actually doing quite decently even after 2 steps of this iterative procedure, but we're not getting all the way to the optimal policy. After 3 steps, we already have converged in policy space. So this points to the fact that we can save all of these iterations of converging all the way to the actual value of the uniformly random policy, because if we're using it only for improvement, we can already improve on this intermediate estimate and get a very good estimate of a good policy. Okay. And an extreme case of this is, why not do just 1 step of this evaluation step and then greedification straight after that? and this is equivalent to what we call value iteration. The way to think about, or the way I think about a value iteration is actually from a different perspective of taking the Bellman optimality equation and doing the same thing that we did with iterative policy evaluation here, and turning this into an update equation. And this, you will see if you go through the steps, that this is equivalent to doing policy iteration with k equals 1 in the iterative policy evaluation step. Okay, and this is the actual algorithm. We initialized as before, randomly or at 0, and then we update now not according to the expected a value under the policy we're trying to evaluate, because we don't have a policy here that we're evaluating. We're just taking the max with respect to what's going to happen in the next step. And the stopping criteria, as before, whenever k plus 1 and k reach the same value, so the value doesn't change, that means in particular that vk obeys the Bellman optimality equation, and by definition that means that we have found v star, which is the value of vk and vk plus 1. Okay, and let's look very quickly at an example of how this behaves in practice. Okay, this is an MDP very similar to the one we've seen before. Just now I only have one terminal state that we're going to transition to. All the rewards as before are -1, so we're encouraging the agent to get out of the MDP as soon as possible, get to this state as soon as possible to transition out of the MDP. And we're going to be considering a discount factor of 1 because this is an episodic setting. And then we're interested in running this new algorithm, value iteration, in this MDP. So we're going to initialize at 0, okay, and then we're going to run k plus 1 is max expectation over what's going to happen next. Previous value. Actually, this should say A. Okay, so the instantaneous rewards are all 1, so this actually update is -1 plus gamma max over A, expectation of these values. Okay, so basically what this says is I'm gonna take an action, I'm gonna transition to this new state, and I'm gonna look at the value that has been generated in the previous iteration, and I'm gonna look at the expectation over all the states that were induced by transition from S given action A. Considering this is a deterministic NDP, this has only one deterministic transition. So all actions have a deterministic transition to a particular state. So for instance, for this state, this action would get here, 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 right? So it's not really an expectation. So basically what this is saying is that I'm going to look at all the neighbors around the state that I'm estimating value, and I'm going to see which of them has the maximum value. And this estimate will take that maximum value. Okay, so the discount also is 1, so we can ignore that one. Okay, the first one is just basically initialization. The second one is trivial too, because v0 is 0 everywhere, so this term will be 0, so everything is updated to -1. Now in the second iteration of v3, it's a bit more interesting, that we're gonna look at, let's say, this state. Actually, first look at, this state. And this state has a transition to this state, a transition to this state, a transition to this state, and a transition to back to itself. So instead of doing an average over these transitions as we did before under the uniformly random policy, we're going to look at which of them produced the maximum value and take that one. So it's going to update the value to -1, which is the instantaneous reward, plus the max over these values, which is 0. Okay, so the update to that would be -1. For all of the others, basically any transition would lead to the same -1 reward and a -1 value function from the previous iteration, from this. And this is added to the -1 from the instantaneous reward. And we continue this process till basically we can see that these two are almost converging. And if you would estimate now v8, then you would have basically perfect convergence. You already see that basically in this step between v6 and v7, basically all states but this one have the right value, and everything else hasn't changed. And in this new step we would just reach convergence, and that would give us both the optimal value function, but also acting greedily with respect to that would give us the optimal strategy. That is it for synchronous dynamic programming algorithms, and this is just tables summarizing the things that we have covered so far. So first we started with the prediction problem, an evaluation of a policy problem, where we took the Bellman expectation equation and turned it into an iterative update leading to the iterative policy evaluation algorithm. And then in the last two sections we've looked at tackling the control problem via policy iteration, and then just now value iteration. One relies on this principle of evaluating the policy and improving it, and then evaluating this improved policy and improving on that one, and so on and so forth. The last algorithm that we talked about, the value iteration, uses the Bellman Optimality equation to go directly for the optimal value function. Some observations. The algorithm based on state value functions, trying to estimate v pi or v star, have the complexity of number of actions to squared number of states per iteration. This is because if you look at the updates, we always have to do this update for each state, and always have to look at the action that we're gonna take after this step, and where we are gonna end up after this state. And the same if we are looking at computing action values, this complexity is now magnified by another factor of the number of actions, because we're always looking at state action, so current state and action take, and what's going to happen in the next step, S prime and N prime. Okay, this can be quite expensive, so in the next section we're going to look at extensions to dynamic programming, in particular asynchronous dynamic programming, that will try to get around this computational issues or alleviate some of these computational issues. So the dynamic programming methods that we described so far use synchronous updates, which means that when we've gone through the examples, you've seen that we update all the table all the time. So we're doing these updates every time we're doing them for all the states in parallel. Okay, asynchronous dynamic programming suggests that we can back states individually in a particular order or in any order, and this can significantly reduce the computational overhead. And also the nice thing about this is guaranteed to converge as long as we do visit all the states, and we continue to visit all the states with a non-zero probability. A couple of instantiation or simple ideas of asynchronous dynamic programming are in-place dynamic programming, prioritized sweeping, and real-time dynamic programming. And we're gonna quickly go through them. They're really simple, so this is the general idea. So in the synchronous version of value iteration, we store two copies, vk and vk plus 1, in order to do this update. Now the in-place value iteration stores only one copy and uses that for the updates. So all the values that we have already updated, those would be used whenever we encounter the next update, rather than maintaining the copy of the values at iteration k. Okay. Prioritized sweeping. The principle here is to select states according to this priority function, and an instantiation, let's say, of the priority function can be using the magnitude of the Bellman error. And we haven't defined it yet, but this is the equation for the Bellman error. The thing to notice here is that for the optimal value function, so if v is v star, this thing is 0. So when we converge to the optimal value function for each state, the priority there would be 0. So we would not be selecting these states for update anymore. Okay, and this basically says that the largest error will be prioritized in order to update the state. This requires knowledge of the reverse dynamic in order to make the updates, but can be efficiently implemented by maintaining a priority queue. Okay, and real-time dynamic programming. Basically, the idea here is to only update the things or the states that are relevant to the agent right now. And what's relevant to the agent right now is debatable, but let's say as a rule of thumb, maybe things around the agent that the states that it will be using, like the current state or the value at future states, that could be used for immediate prediction or immediate decision making. Another way of reducing the complexity of these updates is to look at sample backups. So far in all standard dynamic programming, we do fool with updates. So for every state in the or every state action pair for the queue function, we look at all of the successor states and all of the action that span out of that state. And once we look at all of these conditions on all the actions, we do a full backup for that state. Now, this is effective or can be applied to medium-sized problems, but for very large dynamic programming problems, this might still be quite expensive, or even too expensive to run. Even one full backup, if you have a very large state space or a very large action space, even one full backup might be too expensive. So the idea here is to, instead of doing this full backup of looking at all the actions and all the states that follow state S in order to update it, we're just gonna look at sample versions of this. So we're gonna have only samples of these trajectories, maybe a very small set of the transitions that actually come out of S, but we're gonna use those to make our updates. So we would use sample reward transition of this form, S, A, R, and S prime, just one instantiation of this trajectory, instead of using the full dynamics and the full model to update the whole state. The advantage with that is that it's model free. We don't need to know the actual dynamics and the expected reward in this case, because we're just using the information given by the sample, and it breaks the curse of dimensionality through sampling. We will see a lot more of these, especially sampling methods and implementation of versions of dynamic programming in a sampling context next week, and a lot more methods of making this more tractable and making this more sample efficient. Okay, that is it for today. This is just a summary of what we've managed to cover today. So we started with Markov decision processes to formalize the RL interaction. We've looked at the objectives in MDPs, different notions of return, like discounted, undiscounted, average reward. We introduced value functions, which are expected returns. We looked at optimality principles in MDPs, what are optimal value function, how we can define optimal policies. We also look at the rich structure that value function have, described by the Bellman equations, and we've seen how to use these equations in order to tackle the two classes of problems in RL: evaluation and control. And we've seen in the last half now how to compute the value associated with an arbitrary policy pi, okay, solving the prediction or evaluation problem via a system of linear equation, and or iteratively via iterative policy evaluation. And finally, how to compute the optimal value function using dynamic programming. We've seen two algorithms here: policy iteration and policy iteration and value iteration. Okay, next lecture we're gonna go a bit more deeply into dynamic programming. We're not gonna cover more algorithms, but we're gonna go more deeply into how these work and why this work and when they converge, because so far we've seen only examples of how this work in practice, but we haven't theoretically analyzed them. Okay. Questions? If you have any questions about this lecture or any of the material presented, please use Moodle for questions and the next Q&A session. That is it for today. Thank you for your attention.